Welcome to the Explainer. Today, we're going to pull back the curtain on the hidden world of C++ objects. We're going to explore what's really going on from the moment an object is conceived to how it lives and breathes in your code.
So, what is the secret life of a programming object? Well, we're about to find out. We're going to follow its story right from birth, and along the way, we'll unpack 4 huge ideas: the blueprint, the welcoming committee, its sense of self, and, even its family connections.
Okay, first things first. Before you can build anything, you need a plan, right? In C++, that plan has a very specific name, and it's absolutely crucial you don't mix it up with the final product.
Let's make this simple. A class, that's the architectural blueprint for a house. It spells out where the rooms go, the number of windows, all that stuff. But you can't live in a blueprint. An object, on the other hand, is the actual house built from that plan. It's real. It exists in memory. And here's the cool part. You can build a whole neighborhood of objects all from that one single class blueprint.
So we've got our blueprint. Now let's actually watch an object get built. How does it pop into existence and get all of its initial settings put in place?
I mean, can you imagine creating a new object and then having to manually set every single property line by line? It's not just boring, it is a recipe for disaster. Luckily, C++ has a much more elegant way to handle this.
Meet the constructor. Think of it as the official welcoming committee for a new object. It's a special method that gets called automatically the instant an object is created. Its one and only job is to make sure the object starts out in a valid, predictable state. And you know it's special because, as you can see, it has to have the same name as the class, and it doesn't return anything, not even void.
Now, the compiler is pretty smart about this. This flowchart kind of shows you its stop process. If you don't write any constructors at all, the compiler says, no problem, I'll make a basic default one for you. But, and this is key, if you write a constructor that takes arguments, the compiler assumes you know what you're doing. It won't create a default one for you anymore. You're in charge now.
So, every single time an object is born, this 2-step dance happens behind the scenes. Step 1, the program carves out a little chunk of memory just for this new object. Step 2, boom, it immediately calls the right constructor to run the setup ceremony and get that object ready for action.
All right, our object is created. It's initialized. But how does it develop a sense of self? How does it know to work on its own data when there could be hundreds of identical objects all around it?
Seriously, think about this. Let's say you have 2 complex number objects, right? We'll call them CPL1 and CPL2. If your code calls setReal7, how in the world does that method know if it's supposed to change the real value for CPL1 or for CPL2? It's a real puzzle.
Well, the answer is a little bit of compiler magic. It's a secret invisible pointer called this. When you, the programmer, write a simple line of code like real equals r, the compiler is actually translating that. What it really understands and executes is this dash real equals r. It's adding that part in for you.
This diagram shows exactly how it works. Look, when your code calls cpl1.setR7, the compiler doesn't just pass the number 7, it sneakily passes the memory address of the CPL1 object itself, address 100 in this example, as a hidden first parameter. Inside the method, that address gets caught by the this pointer, which now knows exactly which object's data it's supposed to be working on.
So that's the whole secret. The this pointer is the fundamental link that connects a general reusable method to one specific individual object. It's the magic that lets one blueprint serve countless houses, each knowing who they are.
Okay, so our object is born, it's self-aware, it's doing great. But what if we want to create a new, more specialized object that's a lot like one we already have? Well, instead of reinventing the wheel, we can just extend the family through something called inheritance.
Inheritance is all about creating what we call an is-a relationship. It lets a new class build upon an existing one, inheriting all its properties and methods automatically. It's just like how an apple is a type of fruit, and a fruit is a type of food. Each one gets more specific, but it's still part of the same family tree.
So the terminology is pretty straightforward.
You've got your base class. You can think of it as the parent. It provides all the core features. Then you have the derived class, or the child. The child gets all the parent's features and can then add its own unique stuff on top.
So how does this actually work under the hood in memory? It's pretty wild. When you create a child object, it's not just kind of linked to the parent. It is literally built with a full instance of the parent class right inside of it. Just look at the diagram. The derived one object actually contains a complete base object within its own memory. That's how it's guaranteed to have all the parent's abilities from the get-go.
This brings up a good question, though. What if the child needs to mess with the parent's private stuff? You can't just make it public because then the whole world could see it. The solution is the protected keyword. Think of it as creating a family and close friends level of access. It's a family secret, available to the class and its kids, but kept private from any outsiders.
Okay, last section. Let's look at how all objects of a single class can share information, how they can communicate, almost like they have a collective consciousness, like a hive mind. Let's use an example. What if we wanted to keep a running tally of how many complex number objects are active in our program right now? If every object has its own private little counter, they'll never be able to agree on a total. We need one single, shared source of truth.
And the solution for that is the static keyword. A normal member variable is personal property. Every object gets its very own copy. A static member variable? That's community property. The compiler only makes one copy of it for the entire class, and every object shares that exact same copy.
And this diagram shows it perfectly. See how the three objects C1, C2, and C3 don't have their own little count variables inside them? Nope. Instead, they are all wired up to that one central shared count. When C1 changes it, C2 and C3 see that change instantly.
And it's not just for data. You can also have static methods. These functions belong to the class as a whole, not to any one object. That's why you call them using the class name itself. And here's where it all connects. A static method can't use the this pointer. Why? Well, because there is no this. It's not running on behalf of any specific object.
So there you have it. From the blueprints of a class and the welcome party of a constructor to the self-awareness of the this pointer and the hive mind of static members, that's the secret life of an object. When you understand these core ideas, you're not just banging out code anymore. You're actually designing intelligent, reusable, and really powerful systems.